All right, folks. So let's take a look at 12.5. Okay. So again, there's going to be a lot of writing for 12.5. And the more space you leave yourself, the more steps you write out, I think the easier it will be in case you make a sign mistake or in case you distribute wrong. You can go back and find where you made those mistakes a little bit more easily. Okay. All right. So let's take a look at a little bit of the why. Okay. So far, we've taken a look at a bunch of different conic sections. We've looked at parabolas and ellipses and hyperbolas. And for all of those, it was a little bit easier if the graph was at the origin, because our center was 0, 0. So it made for fewer numbers in the equation. Okay. Now, is it that big a deal to have a shift horizontally or vertically? Not really, and I think you guys handle that very well. But that's kind of what we have right here in this what we know. Okay, so let me share that. Okay. So far, what we learned is if we have a shape and we want to shift it, we could start with our original center here at the origin, and we could move it somewhere else. And the way we describe that is we break it up into two components. We say, all right, we're going to go in a certain direction horizontally, and then we're going to go in a different direction vertically. And even though this diagram says x comma y, if we think about the coordinates of a center, we usually frame that as h comma k. And so again, it was one way that we knew how to deal with a shape that had been shifted, slid to a different part. So maybe we moved it to the first quadrant, or sometimes we move it to the second quadrant, or the third quadrant, or the fourth quadrant. And that's been a skill that you know pretty well since pre-calc. But what's new is this really messy looking diagram over here. Okay, and we're going to break this diagram up into two different ones, so hopefully it'll be easier to visualize. But basically what we're talking about now is we're not just taking, let's say, a parabola and just moving it to a different quadrant, but we're actually rotating it. So maybe the parabola is like kind of on a diagonal. It's not even rotating at 90 degrees. We're straight up moving it to an angle that it would be helpful if we knew that angle. Okay. But anytime we rotate the shapes, so if we rotate this parabola, the equation is going to be much more complicated. Or let's say that we had an ellipse and we rotated it. Okay. The new equation is going to be much more complicated. And same thing with the hyperbolas, which are the equations are already pretty complex. We make them even more complex if we rotate the axis. And so what this lesson is all about is how can we have the rotation, but simplify the equation so that it's not as bad as it could be. Okay. And so what we're going to do is we're going to take a look at this diagram in a little bit more detail. So some parts of this diagram I'm going to keep in, let's make it green. So our original graph maybe has this as a y-axis and this as an x-axis, okay? And on this graph, we have a point. And we call this point P, and we label it x comma y, okay? So I'm gonna just draw the green part below. Okay, so this is our x-axis, this is our y-axis, and we have some point P, and we call that x comma y. All right, so if we said like 2 comma 3 or 7.5 comma 9, that would be the coordinate of point P. And we know we can find that by going horizontal, the x value, and then vertical, the y value. Now, there's a few other parts to this graph that I want to point out. That there's this point here, R, that has the same y value as your point P. And then there is this point Q that has the same x value as your point P. So x comma 0 and y comma 0. So now I'm going to erase the color that I have on the diagram, but we still have our version down here, okay?
Good question. For point R,
Yep.
it doesn't matter, but the y coordinate should still be where the x.
No, it does. It does. This is I need to finish my coffee before class.
Oh, I'm sorry.
No, you're fine. Thank you for pointing it out so it's not documented in history forever. Okay, so I'm going to go back to my diagram and I'm going to erase the green lines and we're going to put a new set of coordinates on there. Okay. Let's get rid of the things that we know. And now, what's new? So let's pick pink because it's nice and bright here. So I've now got a new axis, a new x-axis, this one right here. And I know that this line is not horizontal, but I'm going to call it x prime. And then I have this new y-axis, and I'm going to call that y prime. Now, with this point P, so the same point that I was looking at on the green graph, now we're going to call this point P, but x prime, y prime. And all that means is on this diagonal set of axes, this rotated axes, if I go from the origin out to a certain value on this axis, that is the x value or the x prime value of that point. Similarly, if I go up the y-axis, this y prime, until I get to a certain number, that's going to give me the y prime coordinate of that point. So if I take this pink axis and I draw it down here, it looks something like this. Here's my x prime.
I have a question.
Hold on 1 second. This is my y prime. Yes, what's up?
So it looks like P and P prime are the same, but it's noted as P and then the other points like R prime and then Q's prime also.
It is the same point. It is the same point.
Okay.
Okay. Okay, so maybe here's a good example of that. So my baby sister's name, her full name is Allison, but we all call her Allie. Same person, right? So Allison might be what we call her in a formal setting, like this X comma Y, right? But sometimes it's more convenient to define things when we just rotate the whole set of axes, and the point is the same point as it was on the green one, but we're going to give it a different name, X prime, Y prime, kind of like we call my sister Allie, same person. So green is like Allison, pink is like Allie. It's the same point, but it's a different descriptor of that point. And the reason why we might want to do that is because if we rotate our axes, we still get an idea that we could call this point Q prime, and it has a horizontal component of X prime, comma 0. And it has a vertical component of R 0, comma Y prime. Both the green and the pink describe the same point, but sometimes it's hard if we keep things defined in a regular X and Y plane. And so if we rotate them, then we end up with a situation where it's going to make our graph easier. Okay. Now, the last part of the diagram that I want to point out is it's important when we rotate to know how much we're going to rotate by. Okay. So what tells us how far we rotate is this little guy right down here. Okay. We're very used to having an angle called theta. And what we're going to introduce is a new letter called phi. So phi, okay, let me actually tell you how to write that again. It's like a little O, and then you put like a diagonal line across, all right? So phi is our angle of rotation. So phi tells us how far do we rotate the green one to get to the pink one. And so it's going to be important that we figure out phi so that we know how far we're rotating, and that will give us an equation that looks a lot more like what we've seen in 12.2 and 12.3 and 12.4, but we're going to have some primes in there because we've rotated it to define it in a different way. Okay.
Can I ask one quick question?
For sure. What's up?
So the R for Allie, or the new one, could you write that as R primed and P prime?
Sorry, it should be R prime. Yeah, R prime.
Not the P though? You just leave it as P.
Well, because it defines the same point, we actually call that P.
Okay.
Yeah? Yeah.
Thank you.
You're welcome. Okay.
Can I have one small clarifying question?
For sure. What's up?
So on these graphs, when we're talking about rotating, we actually won't be rotating the graphs. We'll be rotating the axes and then assessing them on that new graph.
Yes.
Okay.
Yes.
All right.
So actually, let's go back to these rotation graphs that I drew earlier. So the first one, this parabola, it's like really nice if I do just a regular XY. But for the second parabola, it would be easier if it was like this. Then we could define our parabola using a regular parabola equation. But do you see how we rotated the green one to make the pink one so that we could keep our equation in our like y minus k squared equals 4px form?
Yeah, so by rotating the axes, you're just going to be changing the distance that each point is from the y-axis and the new x-axis, basically.
Yes, you're changing some distances so that you're preserving the equation form.
Gotcha.
Yeah. So like this second ellipse, maybe we could draw like that, right? The green one rotates to make the pink one. Then I can still write my equation as x squared over a squared plus y squared over b squared equals 1.
Thank you.
Okay. All right. So let's talk about how we go from the relationship between x comma y and x prime comma y prime. Okay, so like how, if we have x comma y, how do we get it into x prime y prime? So there are two sets of equations. One set will tell you how to find x prime and y prime, and the other one will tell you how to find x and y. And I'm going to write down both of those, but then we'll talk about where they come from and which ones we're going to be using. So if we have x comma y, and I have x prime, y prime. If I have x comma y and I want to find the x prime, y prime, then I can use these formulas. X prime equals x cosine phi plus y sine phi. That will find x prime for me. And then y prime will be negative x sine phi plus y cosine phi. If I want to go the other way, to go from my x prime and redefine it in my original green x comma y, then I can use the following pair of equations. X equals x prime cosine phi minus y prime sine phi, and y will equal x prime sine phi plus y prime cosine phi. Now, in the work that we are going to be doing, we're going to be working primarily with this set. So if you have the start of your cheat sheet ready, I would put that on there. If you do not, I would remind myself or yourself at some point when you are creating the cheat sheet that this formula should go on. Okay. All right. Now, I know this is a summer school class, and I know that we do a lot of complicated things, but I think it's also important to pause at some point and think about where these formulas came from. Okay. So I just want to use a little bit of the diagram above to talk about where these boxed equations came from, okay? I don't know, this is necessarily a formal proof. It's more like a derivation, like this is where it comes from, okay? But we're gonna go back and add one thing to the diagram, and that is this. Earlier, I said, hey, there's this new angle phi, and phi tells us how far we rotated our axes, but I didn't talk about this theta, okay? And the theta is actually if I go back to my pink diagram, theta is the angle that the point makes with the x-axis. Okay. What that means is that the angle that point P makes in the green axis is not theta and it's not phi, but it is the sum of those. So this one is theta plus phi. Okay. The last thing I want to tell you is that this distance that I just drew right here, okay, we're going to refer to that distance as a lowercase p. So lowercase p talks about the distance, or if you remember from pre-calc, the magnitude of a vector. That's what that little lowercase p stands for. Okay, so from this graph, the green graph, okay? So from the green graph, if I wanted to define x using my trig functions, I could say that x is the magnitude of that distance, or that distance, times the cosine of my angle, theta plus phi. Okay. And I got that because I could say that cosine of theta plus phi equals x over p, and then I just isolated the p. Now, what can I do with this? I can go back to pre-calc, maybe trig, where I learned about the sum and difference formula for cosine. And I could write this as p times cosine theta cosine phi minus sine theta sine phi. And I'm going to pause here for a moment, okay? I'm going to do the same thing with the y value on the green graph. So the y value on the green graph, how could I represent that using lowercase p and a trig function?
Negative cosine start?
No, not negative cosine. Yeah, it's going to be sine because the y value is the opposite and lowercase p is the hypotenuse. So we have y equals lowercase p sine of theta plus phi. And if I use a sum formula for sine, I can expand that sine of theta plus phi to be sine theta cosine phi plus cosine theta sine phi. Now, this looks kind of gross and maybe not exactly what the formula in that box looks like. And so we have one more step to get that what we have in the green to match the thing in the box. And so what we're going to do is we're going to write similar equations for the point P in the pink axis. And so when I do that, I can define x prime as p, lowercase p, right? Because it's the same distance. Like this blue line is the same distance as the black line because that point is the same, right? Like my sister Allison and my sister Allie are the same person. So that distance is equal. So x prime we can say is p cosine of theta. And here's what we're going to do. We're going to isolate cosine theta. That gives us x prime over p. And everywhere we see cosine theta, we're going to replace this with x prime over p. So we're going to replace it up there. We're also going to replace it down here. And if we do the same thing for the y prime, we'll get lowercase p sine theta, which we can say sine theta is y prime over p. And so everywhere I see a sine theta, I'm going to replace sine theta here and sine theta here with y prime over p. And I think this step is pretty cool, okay? So for the x, I get p times x prime over p cosine phi minus y prime over p sine phi. And check out what happens. This lowercase p reduces with both of the p's in the denominator, because when I distribute, I have to distribute it to both. And then here's what my equation for x becomes. X prime cosine phi minus y prime sine phi, which is exactly what we had in that box. Now, if we do the same kind of reasoning with the y, we have the p on the outside. Instead of sine theta, I put y prime over p, and then I keep my cosine phi. Plus, instead of cosine theta, I put x prime over p, and I have sine phi. And same thing happens when I distribute that p, it's going to cancel with the denominators, and I will end up with y prime cosine phi plus x prime sine phi. Okay, so all of that work in the green and the pink is just to help us understand a little bit where that comes from, like those equations in the box with the stars. Okay. I will not ask you to do a proof or a derivation on the test, but I know that for some of us, we are looking to be either math majors or pursuing a lot more of these math courses here at Mesa or Miramar or City. And so I think it's important that we start to see like where things come from and how people figure out where these formulas come from. Nobody's expecting you to know right now, but when you get to classes like discrete math, which is 245, or linear algebra, which is 254, you do a lot of proofs. And so I think the more exposure you have to this kind of thinking, the easier it is when you're trying to prove other things that you're like, okay, well, I've seen someone use this trick somewhere, so maybe that'll work here. Okay, so this whole page, the most important part is this part right here. You want to make sure you have those formulas. We're going to focus on how to use them. But again, I did want to just expose us a little bit to like where these things come from. All right, how are the brains doing out there?
Good.
Good, kind of. All right.
I think once we see it in
All right, so let's jump into our examples. All right. Now I know we have like 40 minutes of class. We may finish this first example. We may get to the second one, or we'll definitely finish the first one. We may get through the second one. I don't know. But either way, it should be a good start to what we're looking at. Okay. So we're given this equation, xy equals 1, and our goal is to find the equation of the graph relative to the x prime, y prime coordinate system if the axes are rotated through an angle of 45 degrees, okay? So let's identify a few features of this graph first. So I know that I have this xy equals 1, okay? And I'm going to keep that equation the way it is. But I also know I'm given an angle of 45 degrees, and that 45 degrees is my angle of rotation, which makes it my phi. So here's what we're going to do. We're going to write down these two formulas, our x equals and our y equals. And so x equals x prime cosine phi minus y prime sine phi. And then next to it, I'm going to write y equals x prime sine phi plus y prime cosine phi. Okay. Now we're going to take our angle, 45 degrees, plug it into here. X equals x prime. Cosine of 45 is root 2 over 2 minus y prime, and then sine of 45 degrees is root 2 over 2. We're going to do the same thing for y. Y equals x prime root 2 over 2 plus y prime root 2 over 2. I would highly encourage you at this point to factor out any greatest common factor, okay? Like you've been so good about doing with the integrals, like any constants come out to the front. It just makes the actual integral work easier. Same thing here. If we take the time now to factor out a greatest common factor, it will make the rest of the work a lot easier. So my greatest common factor in the x one is this root 2 over 2, which leaves me with x prime minus y prime on the inside. And when I do the same thing for y, I have root 2 over 2 on the outside, and then x prime plus y prime on the inside. All right, so here's what we're going to do. We are going to take everywhere we see an x in our equation, we're going to replace it with this. And everywhere we see a y in our equation, we're going to replace it with this. And if something is just a number, we leave it alone, okay? So instead of xy equals 1, we're going to make this look a lot harder for a moment. So instead of x, I'm going to write square root of 2 over 2 times x prime minus y prime. And instead of y, I'm going to write root 2 over 2 x prime plus y prime. And then I have my equals 1 hanging out at the end. Okay. Now we're going to simplify this. So I'm going to suggest that we take our constants and we bring them to the front and we multiply them. So root 2 times root 2 gives me 2 on the top, and 2 times 2 on the bottom gives me 4 in the denominator. And then I'm really multiplying x prime minus y prime times x prime plus y prime, which will give me x prime squared minus y prime squared. Okay, so I'm just foiling it, and I get x prime squared minus y prime squared. Okay, 2 over 4 reduces to 1 over 2. So I'm going to reduce that And I'm going to distribute it to the two terms I have here. And that gives me 1/2. Let's write it differently. It gives us x prime squared over 2, right? 1/2 of x prime squared minus y prime squared over 2 equals 1. So let me pause here for a moment. How we doing with all the algebra and the substitution?
So far, so good for me.
Okay. This is an easy problem. They get worse. So don't worry about it.
When you got to the factoring point,
yes.
If we, it obviously worked out because our angle was 45 degrees and sine and cosine are the same. If we, let's say it was angle of like 30 degrees and we're going to have different things, should we still worry about factoring or should we just leave it in and then hopefully it'll work out later on?
We're going to factor, but it might just be factoring like a half out or something like that.
Gotcha.
Okay, so if I look at this last equation that I have, x prime squared minus y prime squared, and they're both over 2 and it equals 1, what shape is this?
Hyperbola.
Yes, it is a hyperbola. Okay, so this form is so much easier to recognize. And I know in this case, it wasn't so bad. It was like x, y equals 1, right? And then out came this hyperbola. But for some of the ones we're going to do, we're not going to have any idea what shape that is until we think about rotating it. So here's what we have. All right, let's do this graph of xy equals 1. So xy equals 1 is the same as y equals 1 over x, right? I divide that x over. You guys know what this graph looks like. You've got a graph that looks like one branch here and one branch here. But if I think about my hyperbola, okay, that means that the graph that I have, I actually rotated this 45 degrees. And now if you, I can't turn my, I can turn my tablet, but it won't turn on my screen. If you turn your head 45 degrees, you have a hyperbola in the x prime, y prime plane. Okay. So the xy, it looks like two different branches. And this whole time in your academic career, you're like, you probably never even thought like, oh, maybe this is the same as that other shape I'm learning because we teach them in totally different units, right? But it turns out that 1 over x is a hyperbola. It is just the hyperbola, if we define it in this 45-degree rotation, it actually comes out a lot cleaner if we have to do more math with it, okay? All right, so let's now take a look at things that might be a little bit more complex in the algebra, but the concepts are going to stay the same. Great question. So Patrick asked if it's easily represented in the non-rotated, why would we want to represent it in the rotated? So I chose this example as like let's kind of get our brains warmed up for the processes that we're about to do. But even if I scroll down, you can already tell that like this next equation looks a lot more complicated. And so that's why for more complicated cases, it can be nice to define it in a different way, okay? All right, so before we get to that, we've got some general steps out here for you. Okay, I did notice that some people put a lot of examples on their cheat sheets. Some of you put examples and you annotated your examples, like this is how I got from this step to this step. I squared, I completed the square, then I found my vertex, blah, blah, blah. All of that is really, really helpful, okay? So this piece right here might be a really nice thing to have on your cheat sheet, all right? So in general, we can transform any equation of this form. Well, there's like 6 letters in here. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And the one caveat is that b is not equal to 0. So we have an xy term. Now the xy term is what makes it tricky to complete the square. Because in all the examples we've seen of completing the square, you only have terms with x's or you only have terms with y's. But now we're going to look at cases where there is an xy term. And so our goal is going to be turn it into an equation with x prime, y prime, and no x prime, y prime term. That's going to make it easier for us to graph and to see what shape is it and what are some important points or characteristics about that graph. Okay, so in general, the first thing we want to do is determine the shape and the general form of the conic section. And we're going to do that using the discriminant, b squared minus 4ac. So when you have a situation where you have the discriminant is going to be less than 0, okay? So this first case right here, you're gonna end up, you know that your shape is going to be an ellipse. Now, if you plug things into your discriminant, b squared minus 4ac, and you happen to get 0, that's okay. That's going to give you a parabola. Which means that if b squared minus 4ac is greater than 0, you are going to have yourself a hyperbola. Okay. So by knowing your a, b, and c, which are just right in your equation, your a, your b, your c, you can find out what shape it is before you even get started. Okay, so that's going to be important for us to kind of predict what is this shape going to be like and how do we know that we're getting to the right form. Now, once you've done that, our goal is to get rid of that xy term, right? That's the term that's causing us problems, is the x and y mixed together. So we're going to choose an angle phi such that cotangent of 2 phi equals a minus c over b. And we want to make sure that phi is between 0 and 180. All right, so we're defining the rotation to be between 0 and 180. After we do that, step 3, we're going to write the desired rotation of axes formulas. So these are the formulas that I was like, make sure you get those on that cheat sheet. Okay. And look for that greatest common factor. Some of you are probably way better at the computations than I am. I just find that when I have so many radicals going on that it just makes it way easier if I don't have to worry about them until the end. All right, step 4, you're going to substitute x and y from step 3 into the original equation, just like we did in that first example. We need to be really accurate here. Did we distribute correctly? Did we simplify correctly? And are all of our signs correct? And then at the end, I'd like us to sketch a graph of the equation. And what I mean by that, you don't have to go all out like you did in 12.2 to 12.4. here are a few characteristics I'm looking for each type of graph. If it's an ellipse, I'd like to know where the vertices are and what the phi value is. So what's your angle of rotation? If it's a parabola, I'd like to know the coordinates of the vertex and your angle of rotation. And if it's a hyperbola, I'd like to know the coordinates of your vertices and your angle of rotation. So you don't need to, for problems like this, do directrix and co-vertices and foci. You don't need to do that for these graphs. I just want a quick sketch so that you can kind of convince yourself that what we've done, this rotation of axes, actually gives us a graph that is rotated. Okay. All right, so let's jump into example number 2 and see how far we get today. I feel like I'm really scaring you guys. I don't mean to be so scary. It's just that there's so many places to go wrong. When I was making the answer key, I was like, these problems are so long. So, whew. Okay. So sketch the graph of the equation 41x squared minus 24xy plus 34y squared minus 25 equals 0. So let's do this first. Step 1, determine the shape and the general form of the conic section using the discriminant. So since this is our first time through the problem, let's write out what our A and our B and our C are. So A in this case is 41 because it is the coefficient of the x squared. B is negative 24 because that is the coefficient of the xy term. And C is a positive 34 because that is the coefficient of the y squared term. What is D in this case? Like D as in dog.
0.
0. D is 0. E is 0. And F is negative 25. Okay. I just didn't write those out because I don't need them to find my discriminant and I don't need them to find my angle phi. But I just want us to recognize what those are. Okay. So now let's find our discriminant. B squared minus 4AC equals negative 24 squared minus 4 times 41 times 34. And I believe if you type that all in, that we end up with a negative 5,000. Okay. Now that number falls into this category. Negative 5,000 is definitely less than 0. And so that means that we have an ellipse in this case. Okay. Off to the side, I just want to write something optional. Okay, this is truly optional. That as soon as I identify what shape I'm using, I tend to write down what my goal equation should be. Meaning, if it's an ellipse, I better have an x prime minus h squared over a squared plus y prime minus k squared over b squared equals 1. So like that's my goal at the end. I want something that looks like that. Looks like our regular ellipse equations, but it's x prime and y prime. Mariah, great question. I haven't decided yet. I need to take a look at the questions and kind of go from there. Okay. Okay, you're welcome. All right, so let's move on to step 2. So in step 2, in order to eliminate the xy term, we need to choose an angle phi such that cotangent of 2 phi equals a minus c over b, and that our angle is between 0 and 180. Then we have a decision to make. Okay, so let's find our angle first and then decide which of these two methods we're going to need. So I'm going to write down that equation, cotangent 2 phi equals a minus c over b. And I'm going to plug in my a minus c over b from before. So that should give me 41 minus 34 over negative 24. And that gives me negative 7 over 24. Okay. Now, if you get a case where your cotangent is a nice number, you can find that cotangent, or you can find your angle using the unit circle, okay? Now, in this case, I wanted to choose an example where we had to use these formulas, all right, to kind of check what these formulas are all about. So let's go back to the definition of cotangent. So cotangent, by definition, is the adjacent side divided by the opposite side, okay? And so what we're gonna do is we're gonna sketch a triangle and use that to help us find what this 2 feet looks like. So I know that cotangent is negative, which means that it's in the second quadrant. So I'm going to draw my triangle like it's in the second quadrant. Boom. And this angle right here is 2 feet. Now, when I'm looking for the opposite side, I can label that opposite side as a 24. And the adjacent side, I can label as 7. Now, I kept that minus 7 in the beginning, or that minus sign in front of the 7 over 24, because I need to decide, does the minus go with the 7 or does it go with the 24? So from my diagram, I can tell that that minus sign goes with the 7, not with the 24. Okay. Now, knowing this, how do I find the missing side on the triangle?
Pythagoras.
Use Pythagorean theorem. So we've got a 7 and a 24, and this is actually one of those quote unquote nice right triangles. If you use the Pythagorean theorem, you should end up with 25 for that hypotenuse. Okay. All right. Now to find my sine and find my cosine, I'm going to use these 2 equations that I'm given here. So I've got sine phi. Sorry, hold on 1 second. All right, so to find sine phi, I'm going to plug this into the equation right here. Now, if my double angle is in quadrant 2, which quadrant is my single angle in?
1.
It's in 1. So this plus and minus, really, I know that it's going to be a plus, because if the double angle is in quadrant 2, the actual angle is in quadrant 1. And then I can write 1 minus cosine of 2 phi. So I'm going to go back to that triangle I just drew. I'm going to find the cosine. And so the cosine is going to be negative 7 over 25. And then I divide that by 2. And so let's work this out. I've got 1 plus 7 over 25 over 2. This is going to give me, let's see, 25 plus 7 is going to give me 32 over 25. So I just combine the fractions on the top. and I'm going to divide it by 2. So this is the same thing as saying 32 over 25 times 1/2, which is going to give me 32 over 50. Let's reduce that. We get 16 over 25. And that works out really nice because the square root of 16 is 4 and the square root of 25 is 5. Okay, so that's how we use the formula to find sine of phi. We can use the other formula to find cosine of phi. So cosine of phi equals the square root of 1 plus my -7 over 25 divided by 2. So a lot of my calculations are going to be the same. And so this is going to give me, let's see, 25 minus 7 gives me 18 over 25 over 2. Or, 18 over 50. Or 9 over 25, which works out very nicely to be 3 over 5, not 4. Okay. So we have our sine phi and we have our cosine phi. The reason why we want those is because when we look ahead to step 3, I need to plug cosine phi and sine phi into these equations so that I can substitute into my original equation. So for step 3, let's go ahead and write out those equations, fill in all our numbers that we have, and then I think to James, to James's point, we can look at what might be a good factor to factor out.
Can I ask a quick question before you move on?
For sure, what's up?
So with the formula for cosine phi, you wouldn't multiply the phi by 2 because it's a double angle in there. It's already been taken care of.
Yeah, exactly.
Okay, just want to make sure. Thanks.
Okay, does that make sense to folks? Because I can imagine more than one person had that question. Like in the equation, we have 2 phi, but the triangle that we got is 2 phi. So that's why we can use that angle, cosine and sine, in the equations that we had over there.
So would that be a good habit to always draw out a triangle at step 2?
I think on Monday we'll probably see some where we can just use the unit circle values. And today I kind of wanted to like get the formula out of the way because I think that's a little bit scarier. But yeah, but you can always draw a triangle, but I bet the more questions you do, the more you'll realize, oh, I did need it here, but I didn't really need it over here. Okay.
I have a question.
Yes, what's up?
About sine, to calculate sine, how do we know the positive square root?
Oh, okay. So if my double angle is in quadrant 2, that means that angle is no bigger than 180. So if I take half of that angle, it has to be between 0 and 90. So that's why my sine and my cosine are going to be positive because phi is in the first quadrant.
Okay, thanks.
Okay.
It would still be the same case if your triangle ended up in quadrant 1, correct?
Yeah, if the triangle's in quadrant 1, if you have an angle between 0 and 90 and you cut it in half, it's still going to be between 0 and 90. Okay, So let's plug in all the numbers we have into our x and our y. So x equals x prime cosine phi minus y prime sine phi. This is going to give me cosine is 3/5. I keep my x prime. Minus sine is 4/5. I keep the y prime. And if I do the same thing for y, x prime sine phi plus y prime sine cosine phi, I'm going to get y equals 4/5 x prime plus 3/5 y prime. And keep in mind that I want us to factor out the greatest common factor. And so I noticed that 3 and 4 don't share any common factors. So I just want to factor out the 1/5. And the same thing for the y. 1/5 parentheses 4x prime plus 3y prime. Sorry. All right. So we've done a lot of work, okay? Before we finish class, what I'd like to do is start the substitution process, okay? We will finish the substitution process on Monday, but I want to kind of get us started to see where we can plug some things in. Okay. So here's how I like to substitute. I found that if I just write my equation, if I just plug in everywhere I see an x, I put this, and everywhere I see a y, I put this. If I just plug it right into the equation, sometimes the equation is so long that I can't fit it horizontally all the way on a sheet of paper. I also find that my brain and my eyes get overwhelmed with the length of the equation that I just wrote. And then I feel like I'm more susceptible to making sign mistakes or distribution mistakes. So what I'm going to do is this. I'm going to take the first term. Let's pick a good color. I'm going to take this first term, 41x squared. And I'm going to write it here. And across from this is where I'm going to do my substitution. So 41 stays, but then I need 1/5 3x prime minus 4y prime squared. And then I'm going to continue to work across. So everything for that simplified 41x squared with x primes and y primes will be all in this same line. The next line, I put the next term. So here's my 41x squared. I leave myself enough space, and then the next line, I'm going to put negative 24xy. And I'm going to substitute in the x and the y and keep that negative 24. So negative 24, 1/5 3x prime minus 4y prime times 1/5 4x prime plus 3y prime. And then I'm going to simplify across. And I'm going to do the same thing for the 34y squared. And then the 25, I don't have to do anything with. I can just leave it, okay? Okay, so we're going to stop here for today. Okay, we're going to stop here for today. But if you want to think ahead about where we're going to go on Monday, we're going to do a bunch of foiling, a bunch of combining like terms, and trying to get this whole equation to have something that looks like this, okay? So again, we're going for a form that looks very graphable, but it just happens to be in that rotated axis, all right? So we'll have x primes and y primes instead of x and y. If you are wanting to get a little bit ahead this weekend, you can certainly try foiling these out so that, you know, when we come back on Monday, you'll have at least seen it a little bit. But if not, and you want to focus more on your quiz 6, then that is totally fine, okay? So I'm going to stop the video here.